In this lecture, we discussed two things. We discussed linear transformations and linear combinations. So linearity it's a big deal. Therefore, the word linear is part of the title of this subject, linear algebra, and the algebra of things, objects that are linear, um, relies on some of the properties that we are formally addressing now. However, we have been learning a lot of things that involve scalar multiplication and that involve addition. Two of the crucial ingredients to address linearity. These operations are at the core. If you're going to define a vector space, sure enough, there are 10 properties that are required. However, these 10 properties that define a vector space, are defined in terms of two operations. And without the definition of these operations, there's no use in working out and verifying proof or disproof, if these 10 properties hold true or not. The two operations are addition and scalar multiplication. So let's consider a transformation T, and we consider vectors u sub 1 through u sub t, which are in the domain. And now we're going to consider scalars, typically called scalars alphas, but now we're going to use the notation a sub 1, a sub 2, all the way through a sub t. So what this theorem tells us is that when we consider the transformation evaluated at a linear combination where the scalars are given by a and the a's and the u's, that evaluation is equal to a1 image of u1, a2 image of u2, all the way through a sub t image of u sub t. So in other words, when we consider the image of the linear combination, here summation of a sub k u sub k, when k runs from 1 to t, that itself becomes a summation that looks like a sub j t of u sub j. And so here we would say that j as an index runs between 1 and t. So the linear transformation evaluated, the linear combination, is itself a linear combination. Here each object t of u sub j is a member of the codomain, right? And so V, the codomain, is assumed to be a vector space. So this right hand side here is another linear combination, but this is a linear combination, which is a subset of which is a member of the codomain. So this is a natural extension of the definition of linearity. Linearity requires addition and scalar multiplication, and we know that a linear combination involves both of these things at the same time, and this is a very neat way of addressing both. You may wonder, why did I change the indices? It doesn't matter. The summation here on the left hand side has index k. What all that matters, I could have written here k's instead of j's. I just did that. I don't know why I did it that way, but do not be discouraged. You could use the same indices in this case. So this is a natural extension or generalization of the linearity of this transformation when acting on members of the domain. So this theorem tells us that we consider first a basis for the domain. So the idea of this theorem here is that this domain U, okay, U is the span of the set B. So B spans U, and in fact the dimension of the domain here, the dimension of the domain, just by using what we're assuming here, is equal to n, right? Because there are n elements in this basis of the vector space U. And on the other hand, we have as many elements as the dimension of the domain, as many members as we have in the dimension of the domain of the vector space V. These are not necessarily a basis for the codomain, and so this is not necessarily distinct, meaning the domain and codomain could be the same set. And so suppose we have a basis for the domain, suppose we have as many members of the codomain as the dimension of the domain. And so the big deal here is that there is a unique, this is something very common in mathematics, uniqueness. There is a unique linear transformation such that each member of the basis of the domain is mapped to one of these vectors that we're considering. There is a way of mapping each basis element to a vector in the codomain. And that unique way is by the existence of this unique linear transformation. So we're going to consider this example which maps C3 into C2. So here clearly the dimension of the domain, here the domain is C3, and that dimension is equal to 3. So we need to come up with 3 members of the codomain, but we note that we notice that the codomain is another vector space. They don't have the same dimensions, right? So the codomain has dimension 2. So we this is an example, right? So suppose that we have a map, a linear transformation, such that when the linear transformation is evaluated at 1, 0, 0, this is evaluating t at e sub 1. This is one of the standard unit vectors. And here we want to remember that the vectors e1, e2, and e3, these are the columns of the identity matrix, the 3 by 3 identity matrix. This set, okay, this set is a basis for C sub 3, okay? And so here we have information about the transformation evaluated at basically what we're writing here is t of e sub 1. You can also write that as t of e sub 1. That is equal to 2, 1. So we don't know explicitly what is the transformation t, but we have information about the evaluation, the image of a basis element, of a basis vector of the vector space C3. And so suppose that also we have information on what is the transformation evaluated at e sub 2. This vector here is e sub 2. And then that we also have information of the transformation evaluated at e sub 3. Even though we don't know the formula of this t, we have information, important information about these evaluations at each basis element of C sub 3. And so this is what we were noticing before, that this set B has the property that it spans C sub 3, right? So the previous theorem tells us that there is a unique linear transformation that behaves in such way, okay? And this bears the question, well, if we have information on the basis elements, how about computing other images, right? How about, remember, we are considering T from U into V, and so we're assuming that U is C sub 3. What if we can use the information on the basis elements of C sub 3 to calculate the images of other members of the domain? So let's consider this vector here with entries 2, minus 3, 1. And then let's note that because we know a basis, the standard basis, we can think of this as 2 times E1 minus 3 times E2 plus 1 times E3. So in other words, we have 2 times E1 plus minus 3 times E2 plus 1 times E3. And so if we consider the evaluation, so what we want now is to evaluate T. It's like evaluating T here on the left, and T of this would be T of that, and because of properties of linearity, this becomes 2 times T of E1 minus 3 times T of E2 plus 1 times T of E sub 3. Okay, This is exactly because of one of the theorems we just discussed. And so this evaluation becomes 2 times this vector, given that this vector here is precisely the transformation evaluated at E1, and this vector here is the transformation evaluated at E2, and this would be T evaluated at E3. Okay, and so with this calculation, so we obtain that in fact the image of W is the vector 13 minus 10, because we end up actually carrying out the calculation of this linear combination, right? So we compute each of these vectors. So this would be 4, 2 added to 3 minus 12 added to the vector 6, 0, and that precisely leads to this vector. So what happens if we now try some other vector, which we express as a linear combination of the standard unit vectors, and we want to calculate the image of this arbitrary vector, in this case called x. So T of x becomes this linear combination, 5 times vector 2, 1, 2 times vector minus 1, 4, and then minus 3 times vector 6, 0, and then we add them up and get this result. So we would say that any other value of t could be computed in a similar manner, even though we don't have the exact formula. We could calculate some other evaluations, because we do have information of the transformation evaluated at elements of a basis for the domain. So we consider a map between the polynomials of degree 3 and mapping polynomials of degree 3 to matrices with 2 rows and 2 columns, and then consider a subspace of P sub 3 given by polynomials of degree 3 that have roots at 1 and 3. So a basis of this subspace is given by this set with these 2 polynomials. And now we're going to consider this transformation S going from P3 to M22. So we consider the evaluation of the transformation at these basis elements, okay? And when we evaluate, this is all information we have. We don't know what is the formula, but we do have information on this evaluation. So the theorem tells us there is a unique linear transformation with these 2 values. Let's consider, for sake of illustration, this member of P sub 3. You can verify that both 1 and 3 are roots of this third degree polynomial, and finding the scalars, so that this is key here, finding the scalars that allow writing Q as a linear combination of the basis members, basis vectors. Well, that on its own, it's something that I'm skipping here, but you can set up this problem and find such scalars, and you find that Q can be expressed as this linear combination, and the theorem implies that Q is indeed a linear combination of its own, which is minus 5 times this matrix plus 2 times this matrix, and this is making use of the information we had. And that information is basically the values of the evaluations of the transformation at members of a basis for the domain. So this theorem is quite useful, and we can say that this theorem basically states that it is enough to know what a linear transformation does to the basis. That's it. That's all we need to know. We don't really need to know the exact formula, explicit formula, but if we know the evaluations at the basis elements, then basically we can work out with the linear transformation.